There are two trig functions that come up often in calculus, and that is what we want to look at today. They are called the two special trig limits. So these are two formulas that you should eventually memorize. The first says, if we have the limit as x is approaching 0 of sine of x over x, that limit is always going to go to 1. Now, in calculus, you are taught that the first thing we do is take x is approaching 0, plug in your x value to see what y value we get. Here in this case, though, if I take 0 and plug it in for x, I have a sine of 0 over 0. Well, that gives me the indeterminate form of 0 over 0. And so you can take for granted at this point in time that this limit will always equal 1. If you wanted to prove it, you would prove it using a theorem called the squeeze theorem, which is not included in this video. The second formula says we have the limit as x is approaching 0 of 1 minus cosine x over x. This formula will always go to 0. Now, on the top equation, notice if I reversed it and I actually made it the limit as x is approaching 0 of x over sine x, well, 1 flipped is just 1, so the limit of sine of x over x is actually the same thing as the limit of x over sine x as long as x is approaching 0. If x approaches any other value, it would have to be a different value for your limit. However, I cannot do that with the second equation, and that's because if I flip where the 0 is, then it would be in the denominator of a fraction, and I cannot divide by 0, so this fraction cannot be flipped, whereas with the sine of x over x, that one can be. So the first example is going to use one of those two new formulas. This one says we have the limit as x is approaching 0 of tangent x over x. First step with limits, no matter what, is always take 0 and plug it in for your x. So in this case, I would have tangent of 0 over 0. Well, based on the unit circle, tangent of 0 goes to 0. And when x is 0, we have the denominator 0. This is your indeterminate form that says, hey, I really do have an answer, but you're going to have to do more work to actually find it. So in this problem, what I want to do is I want to go ahead and rewrite tangent as sine over cosine. So I have the limit as x is approaching 0 of sine over cosine, and that is all being divided by x. Well, it looks like I just made it worse because now I have a complex fraction, but I can go ahead and rewrite this as the limit as x is approaching 0 of sine of x over cosine x times, and then technically you have to realize you have a fraction divided by a fraction right here, so I can divide the two fractions by flipping the second and multiplying. So multiplying by 1 over x, and then thinking about our two new formulas, we see that we have a sine of x and then a divide by x, and x is approaching 0. So I can use the first special trig limit where we have the limit as sine of x over x as x goes to 0. But here's the thing, I have to go ahead and kind of manipulate this a little bit. So what I'm going to do is I'm going to rearrange the terms that are being multiplied. And that's because when you're multiplying two numbers together, it doesn't matter the order that you multiply. A times b is the same thing as b times a. So I can basically reverse where the x and the cosine x are located and just swap them out because they're just being multiplied. So now notice I have the sine of x over x as x goes to 0. That's going to go to the new formula which goes to 1. And so now my limit will become 1 times 1 over cosine of the x, which is 0. And based on the unit circle, cosine of 0 is 1. So I have 1 times 1 is 1 for the final answer. That would be the limit as x is approaching 0 of tangent x over x. The next one might throw you off a little bit. So this one says we have the limit as x is approaching 0 of sine of 4x over x. And that 4x is what kind of messes up everybody. Now, in terms of the special trig limit, basically it says if you have the limit as x is approaching 0 of sine of something, I'm just going to call it a, over that same something, which again I'm just calling a, that's always going to equal 1. So basically, if the inside of the sine matches my denominator and x goes to 0, then my limit will go to 1. So if I have sine of 4x at the top, then I need a 4x on the bottom. So I need a 4 in the denominator, so I'm going to multiply by 4 in the denominator. But I can't just randomly put in a 4 on the denominator and then nothing else anywhere else in the problem. I can't do that because mathematically you have to multiply by 1 in the skies. So whatever I put on the bottom, I'm also going to multiply on top. That way I'm multiplying by 1 in the skies. So then I haven't evaluated the limit yet, which means I need to keep the limit notation in front. So I have the limit as x is approaching 0 in front. Still have the sine of 4x. I'm going to go ahead and multiply this 4 and this x together to make 4x underneath. And then notice when I move this 4 over with that x, I still have the 4 in the numerator at the top. So that's still being multiplied over on the side. And so technically you could put this over 1 if you'd like, but you don't have to. And then based on the special trig limit, as long as we have sine of something over that same something, that part is going to go to 1. So this portion, because x goes to 0, goes to 1. So my limit says that this is going to equal 1 times 4, and so my final answer is 4. The next example looks like the second special trig limit. So notice the only difference is I have 1 minus cosine x being squared, and the original special trig limit says I should only have 1 minus cosine x over x. So what I can do is I can go ahead and expand it. That will give me the limit as x is approaching 0 of 1 minus cosine x times 1 minus cosine x all over x. And if you like, you can go ahead and split this. So we have the limit as x is approaching 0 of 1 minus cosine x over x times 1 minus cosine x. And based on the special trig limit, the second formula says as long as we have x approaching 0, 1 minus cosine x over x is going to approach 0. So then my limit goes to 0 times 1 minus cosine of, I'm going to plug in the x as 0, and cosine 0 on the unit circle is 1, and so I have 0 times 0, which is going to go to 0. The last one definitely looks weird. We have sine of 2x over a sine of 3x. So again, if I plug in 0 first, I have sine of 0 over sine of 0. Well, that's 0 over 0, which is the indeterminate form. So I'm going to have to use one of the two special trig limits. Definitely I'm going to use the one with sine. And so I'm thinking about the limit as x is approaching 0 of sine of the inside, which I'm going to call a, over whatever the inside is, which is a. That's going to go to 1. But because 1 flipped is still 1, that is the same thing as the limit as x is approaching 0 of a over sine of a. So applying that to this problem, what I need to realize is if I have a 2x in the top, I need a 2x in the denominator. And then the sine of 3x is going to look like the second half over here, where as long as I have sine of 3x in the bottom, I need a 3x on top. So I'm missing a 2x in the denominator, and I'm missing a 3x in the numerator. So I'm going to go ahead and rewrite the problem. So I have the limit as x is approaching 0 of sine of 2x over sine of 3x. And I'm just going to deal with the 2x for a moment. So if I have sine of 2x on top, I need a 2x underneath because that's the inside of the trig function. But I can't just randomly multiply by 2x on one side of the fraction. I have to multiply by 1 in the skies. So I'm going to multiply by 2x on top. And then I'm going to deal with the sine of 3x. So that's going to look like the second half of the equation, where sine of the inside has to have the same inside on the top. And so if I have a 3x in the bottom, I need a 3x in the numerator. So I'm also going to multiply by a 3x on top. But again, I can't just multiply by 3x on one side. I have to also put it on the other side of the fraction, That way I'm multiplying by 1 in disguise. Then I can go ahead and start rearranging. So I'm going to rearrange this so that everything matches up. I'm going to keep the same color so hopefully you can follow it. So we have the limit as x is approaching 0 of sine of 2x. I'm going to move that sine of 3x to the next fraction. And then with the 2x, I need that underneath the first part, so I'm moving that over. But I still have the 1 up here in the numerator, so I'm just going to put that at the end. Again, I'm color coding it so you can follow it all. And then for sine of 3x, I need a 3x on top, so I'm moving the 1 from the numerator here just over. And of course I'm allowed to do this because you're allowed to multiply in any order, so all I'm doing is rearranging the multiplication. And then I still have that 3x in the denominator, so I'm putting that in the denominator over there. So all I did was break apart the 3x to here, break apart the 2x to there, and then split apart the sine of 2x and sine of 3x. Here's why I did that. Now I have sine of 2x over 2x, so the inside matches the bottom, and according to our formula, that's going to go to 1. So this part will go to 1, and then sine of 3x with the 3x on top matches the second half of the formula. That's also going to go to 1. So that goes to 1. And then notice with the 2x and the 3x, the x's actually cancel out. So those will cancel out, leaving me with 2/3. So after all that work, my limit goes to 2/3. Which some of you may realize, oh, if I look at the original problem, I have sine of 2x over sine of 3x. That's just the ratio of the inside. That'll actually always be true. This is not something I want you to memorize because I need you to understand how we got there with the work. But you can always check your answer because whatever the ratio is here, that'll be your final answer as long as x is approaching 0. If x approaches anything else, you just plug it in and get your answer from there. So hopefully that helps you understand how to apply limits with two special trig limits and gives you a couple examples to illustrate that.